Start recording. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream, except for tonight. And the reason for that is we have come to the point, they don't happen that often on the stream, but we have come to the point where we need to explain a computer science fundamental. And so today is going to be one of those days where we talk about it on the whiteboard, or blackboard in this case. And so we're not really doing any game programming right now. We are really just going to be talking about that. So if you care about what order notation is, or rather if you don't know if you care, that's really the more important part. If you don't know if you care or don't, like you don't have a real firm enough grasp on it to know whether you care or not, this is probably the place to be, because you will have that answer in just a few short minutes. So let's go ahead and get started on that. And I will go over here to the Blackboard day 231, order notation. All right, now first I want to start off with a really big caveat, which is to say that people who do like sort of the formal discipline of computer science care about these sort of things a lot. And in fact, order notation is just a very small scratch of the surface of the sorts of theoretical computing things that they care about. I am not a theoretical computer scientist, and so all of the things that I'm going to say on this stream are for the working programmer, if you will. We're going to be talking about order notation from the perspective of someone who's trying to make code run on a machine and cares about its performance characteristics. That is not all there is to this story, and so a number of the things that I say are going to be very simplified, or they're not going to really go as far as you would want to go if you actually care about theoretical computer science. So what I would say is, as we are going through this, if you find yourself curious about these sorts of things or feel like you're kind of interested in it in general, you may be interested in theoretical computer science just as a discipline, and I would encourage you to go read more about it or watch some lectures online. Maybe people have some recommendations they'll post on the Handmade Hero forums that you could look for to learn more about it, because it is a really interesting field. It's not one that necessarily has immediate ramifications for what we do day to day all the time, but sometimes it does, and I wouldn't be talking about it if it didn't have ramifications to what we're working on right now in our code, for example. But it's also just a theoretically interesting thing, and so if you do find that, please don't think that what I'm saying here tonight is really the full picture. It's not. It's just the basics to help you understand how to apply it and how to use it. The more richer, more interesting parts of it are, well beyond my computer science background, certainly, and they're best left to someone who's a professional in that field. So that caveat aside, let's talk about order notation. Now, you've seen it even on this stream. We've mentioned it briefly, and I gave Kurt a capsule overview of it, but I want to sort of get it out of the way now once and for all, and we're on sorting, which is kind of a classic place where this thing would be covered. So let's talk about that. Now, you've seen order notation before, probably something like this. Typically, it has an O, a large O, capital O. That is not a 0. It is an O. And it's got a parentheses, and then there's something in the parentheses, oftentimes involving an N. It can involve other things too, but oftentimes you'll see something like this. And people will often say it. They'll say, oh, that's ON, or they'll say ON squared, right? You'll hear them say this out loud. When they say ON squared, they're talking about that, right? So people will typically say the O, and then they'll say what's in the parentheses, and that is what they're talking about. And we've talked about this on Handmade Hero, and we've used the term, but we never covered it in detail. So what is it? What is this notation really mean? Why do we care? Blah, 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 right? Okay. What this is it's an attempt to talk about how an algorithm scales with the amount of work that you expect it to do. So what we talk about when we talk about work is we typically talk about like some kind of a unit, and the unit is what's represented by n. And so, for example, we're talking about sorting right now. The number of individual elements that you expect to sort might be like the unit that we're talking about here that refers to n. So when we say n in sort of the context of order notation, what we're saying is how many units of work do you expect this to do? In the sort, how many things do you expect to be sorted? If you give me a list of 10 things to sort, then in terms of order notation, typically that means that the n, when we say n, means that 10, right? Okay. Now, why do we say n? Why don't we just say 10? Well, the reason is because typically when we're talking about order notation, we want to know how something scales. So we're inherently saying, we don't know, we don't want to say ahead of time how many work units we're doing. We want we want this branch of the math to tell us how our algorithm performs across the whole range of possible workloads it could be assigned. And so that's where the n comes from. The n comes from us saying, we're not going to say ahead of time how many work units we want to do. We want you to tell us something about this algorithm so that we have an idea of how it will perform as we scale up the amount of work. Very, very basic. Let's take it up to a slightly more complex level. All right. Now, if you were to just think about this from a non-computer science standpoint, from a non-programming standpoint, as just a naive person perhaps looking at this problem, you might say something like, well, I don't know what you mean by how does it scale, right? Because in the real world, typically when we talk about specific things that a human might do, scale is always what you might call linear, most of the time, okay? What that means is that every time I ask you to do a certain amount more work, it will take you a certain amount more time, okay? If I'm asking you to put stamps on envelopes, right, then if it takes you 1 minute, and don't ask me why, to stamp one envelope, right, then we would often expect it to take 5 minutes to stamp 5 envelopes. That's just the kind of thing we're used to seeing as humans. Now, it's not always true. There are things we could pick that wouldn't be true, right? But I'm just trying to give you a little bit of a foothold into why it may be non-intuitive, some of the things we're going to talk about, if you've never seen any of this before. If you have seen it before, it's probably intuitive by now, but you get the idea. Okay, so that is what we would call linear, and the reason we would call it linear, right, is specifically because of this whole concept up here. If we were to write an equation that talked about, or not even an equation, just an expression that talked about how long it took you to do something, well, this obviously is my n, right? The number of envelopes is the number of work units. So I am talking about n envelopes. And if, for example, I made a slightly more complicated thing, so it took 2 minutes per envelope, so it took 10 minutes for 5, right? Then you could easily just if you've had any math at all, instantly tell me how long it takes to do n envelopes, correct? You would say it takes 2 minutes times on n, right? That is the time, right? And furthermore, I might leave the units in there and say n envelopes at 2 minutes per envelope. The envelopes cancel, and I just get 2n minutes, right? That is why we might say it is linear, because the factor, right, the exponent, I should say, not the factor, the exponent on our n is 1, right? It's linear. It looks, when I graph it, like a line. Here is my, number of envelopes. Here are my minutes. And this goes up, and I said it was 2n, so it's probably a little more like that, right? But it's a line. Okay. Now, if all the things humans did that are typical like this, if that was all that computers ever wanted to do, we probably never would have developed order notation at all. In fact, we probably wouldn't care, and I wouldn't be spending this stream time explaining it to you. But computers often do things that are much more complicated than what humans are expected to do. In fact, that's why we have computers. If they didn't, then why do we even have them, right? And oftentimes what happens is we will produce algorithms that are not linear. So let's take an example of what that might be. And I'll give you an example of how it could happen even in the human world. I am going to give you n envelopes, like I did before. And now what I want you to do is I want you to go through and tell me if any of these 2 envelopes are addressed to the same person. Right? I would like you to check to see if the address on any given envelope matches the address on any other envelope. And if it does, I want you to tell me. Very simple, right? Well, even if you're a human, you've got a problem. The most naive way to do this might be to pick up one envelope and look at all the other envelopes one at a time, and see if they match. If they don't, you know that that envelope is fine and you put it aside. You then pick up the next one and you go through it. How long would that take you? Right? Well, you can imagine if we could quantify the amount of time it took you to look at one address and the other address and see if they match. Let's say it took something like 5 seconds to do that. So 5 seconds per pair. Then we would simply need to know how many of those do you have to do. Well, you're going to take the first envelope, right, and you're going to compare it to all the other envelopes. That would be n of these comparisons, right? So that's n comparisons for the first envelope alone. Then we would have to add to that, right? We put that envelope aside. We don't need to look at it anymore. We'd pick up the next one, and we'd have to look through all of them. So now, how many pairs are there again? Well, now we have one less pair. So really, it would be something like n minus 1, right? And we'd keep going all the way down, right? Until we got, to just till we got this all the way down just to 1, right? In other words, we have to do n minus 1, n minus 2, n minus 3, n minus 4, n minus 5, until we got all the way till this was n, right? And so if you look what happens as this kind of goes out and out and out, depending on how big n is, what you can see here is that if we were to add up all of the n's, right, if I was to distribute here, I'd get n, and this is the plus, so n minus 1 plus n minus 2. I'm going to get as many n's, because remember, I've got as many terms here, I've got n minus 1 of these terms, right? Because until I get n all the way down to 0, I got to keep going. And so that means there will be n terms, or n squared, right? Which means that the number of envelope pairs I have to look at is going to be proportional to n squared. Now there's a subtraction in here, right? I have n minus 1 times n as well that gets removed from there. But, I'm sorry, not n minus 1. I have n minus 1, the constant, that gets removed from there, right? Because these constants get removed from there, right? But those don't actually, subtracting a single n from an n squared is just going to give you, n squared minus n or something like this, right? It's only going to take away a very small amount. And so typically when we're working on the order notation for something, meaning how long we expect something to happen, oftentimes you don't even really care about that part of it, if that makes sense, right? And so usually this part is the only part we concentrate on. Now, why is that? Why is that the only part that we concentrate on? Well, first, let me just observe, this is the nonlinear part here, right? The fact that we now have an exponent on this thing that is not 1, that means that this is nonlinear in the amount of work that we have to do, even for a human, right? A human has to do this much work. There's nothing special about it being a computer or otherwise. So somewhere around the proportion n squared is the amount of work you might expect to do. And so if it took 5 seconds per pair, you're thinking of something like 5 seconds, right, times something like n squared. And if you want to be precise, maybe you do n squared minus n minus 1 or something like that. Maybe you try to make it a little more accurate, but this is about as accurate as you need to be for our purposes. So even if you didn't have something that was this clean, as long as whatever the thing is that you created, as long as you could clearly see how many n terms there would be, that would be enough for our purposes. So anyway, so just ignore that for now, because like I said, it's not important. You'll see why in a second. But point being, it'd be something like 5 seconds on the order of n squared, right? So it would be 5n squared seconds, and that's how much work you would expect it to be for n envelope comparisons. Now, why do we care about that? Well, the reason we care about that is because you'd imagine what graph shape this might be. Here was the graph shape of something that was linear, and as you can see, as we add more work to do, we expend more time in exactly that proportion, okay? But if we had something that was n squared, that's going to look like a parabola, right? It's going to look like this. And it gets to a point where it's extremely, extremely steep. The difference in computing power, or human power in this case, human time, this might be an hour, but just add a few more envelopes, and all of a sudden you're at 2 hours, right? Whereas before, that same number of envelopes added would only cost you another 5 minutes or something, let's say, right? So what that means is there's a very real conceptual difference between these two tasks. And the conceptual difference is that in the linear case, I can always, without even knowing how many envelopes we're talking about, I can always tell you the exact amount of time extra you will need to do a certain number more envelopes. It's always the same. Want to do 5 more envelopes? It's 10 more minutes. With anything that is superlinear, right? It's not n to the first, it's n to the second, n to the third, n to the 10th, heaven help you. No longer true. Now there is a breaking point in the algorithm. There is a point where the curve gets so steep that even just adding a single extra envelope would be so expensive that you could never hope to do it. Right? That's the bummer of superlinear algorithms. Now, let's go back down here to what we were talking about with order notation. Hopefully now you can start to see why we might care about the concept of order notation, because order notation is precisely the thing that boils things down into how long we expect them to take as they scale. So when we say that something is O(n), we are talking about the linear case. When we say that something is O(n squared), we are talking about the squared case. We are literally talking about the things we just did in our simple examples. So an O(n) algorithm can be expected to be scaled very gracefully. As I add more things, I spend more time, exactly proportional to the number of things I added, and I can keep doing that forever without ever expecting to hit a breaking point. The time just keeps going up proportionally, and off I go, right? Very, very predictable, very stable, very easy to deal with. It's nice. As soon as I start talking about something that doesn't have that, that is superlinear and then has something in that exponent, bad news. That's very bad news, and the reason that it's bad news is because that n squared means that there will be a breaking point. I don't know where it is, but somewhere there will be a breaking point where I will no longer be able to add computing resources or human manpower, whatever it is that I'm feeding into this algorithm fire. I will some point reach that point of the curve where the game is over, right? And it's here. And just adding even one more envelope just caused this ridiculous amount of nastiness, right? Whereas I was used to doing it here. So I'm scaling, I'm scaling, I'm scaling. Oh, it's kind of working, and then forget it. Now it's like it's just everything ground to a halt, and I can never process any more envelopes, right? So that is the basic idea behind order notation. It's to say, let's break an algorithm down into the fundamental size of its input. How many work units is it expected to do? And then let's classify it based on how it will scale. Now you'll notice what I didn't include in the order notation is something like this 5 seconds here, right? None of that stuff made it down here. Why? Because I don't care, right? I just don't care. I'm talking about how it scales. Now, that doesn't mean that CS doesn't ever talk about this. It does. Oftentimes it will say, well, there's a constant factor, right? So when I say something's O(n) or O(n squared, what I'm really talking about usually is that it's O some constant times n, or O some constant n squared. And they will talk about that. When they actually do their proofs and derivations, they will often even compute what the C is in some sort of, if they're talking about some abstract machine, they might even include it, who knows, right? But the reason that we don't actually care about that very much when we're talking about order notation is because order notation is about how things scale, and the constant doesn't affect the scaling. The constant just affects how bad the overall cost is, right? But it doesn't change where that breaking point really is, because the breaking point is about the steepness of this curve, the change, I should say, in steepness of this curve over time. And if I was to elongate, if I was to multiply this curve by some constant, yes, the curve, gets more like that or whatever, but the general scaling, sort of look of the curve doesn't change. It doesn't go like that, for example, where the breaking point happens much sooner. It's just a gradual sort of stretching of the curve that keeps its exact same shape, right? So typically, yes, does the constant factor matter to people when we're implementing? Absolutely, because that constant factor, when we start to talk about algorithms, is how many instructions it takes to do each iteration of this loop or things like that, right? So we do care about the constant factor come implementation time. But when we want to talk about how something scales, we don't care what the constant is. We just want to know this, because that's the answer to the scaling question. The performance question is more complicated. That involves the constant factor, but the scaling doesn't. And so what you know is that if you have an ON thing, no matter what the constant is, it scales. It may be really slow, but it's never going to hit a point where it becomes drastically more slow, right? It's always going to be the same amount slow when I add new stuff. N squared, not true. Could be extraordinarily, extraordinarily fast, very, very low constant, but I can give you enough items until where adding one more to it would be a breaking point for you, no matter how fast the algorithm is. And that's the important part to internalize about order notation. It's telling you how something scales out to infinity. Like as we add more and more and more units, what will happen to this thing? And the constant doesn't come into play there. The constant just is a thing that talks about the reality of a specific implementation and how fast it will run for a given number of units, yes. But in terms of knowing whether it will scale, not relevant. Okay. So how does this translate into code? Well, it's very, very simple to understand how this translates into code, actually. It's a for I loop, basically. I mean, essentially, you can think of things as being that simple. It's like, okay, I've got a for I loop. I'm going to say for I equals 0, I is less than, n plus I. That is ON, right? I am going to iterate over n items. Done. This is an ON thing. It will scale linearly. Everyone's happy. What if I do this for j equals 0, j less than n, plus j, and now this is where my algorithm takes place. Uh-oh. There's an n loop. This is an n loop, right? Every time I go through this loop, I have to go through all n items again. Suddenly, we've hit n squared, right? And so really, it does directly translate conceptually into code. It is not a purely theoretical thing. It is all theory that you can use in a pure theory sense, but it actually is exactly translatable into code. It's the loops in your code, right? Or something you could write it with tail recursion. There's recursive functions have this property as well, like how many times will they recurse. That's also could be an n, right? But basics, loops. How many nested loops do you have? One level of nested loop, on, two levels of nested loops, n squared, three levels n cubed, n fourth, and so on and so on, right? All right. So that's the basics of order notation. Okay, let me tell you a few other things about it. Let me check my time. I've got about a half an hour, so let me tell you a little bit more about it so that you can have a little bit of a foothold into it if you would like to go explore it more on your own. Because like I said, it's a very, very rich theoretical area that computer scientists are working on all the time. And you may find it interesting to go read about some of the stuff that they've done. Okay. So there's other things. So let's talk about first that ON. What does it really talk about, right? Well, this may be a very simplistic view of what it might look like in the code, because maybe there's a break statement in here, right? And that break statement is inside some if, and that if triggers sometimes. That means that when I run this program, I may not actually execute n squared loop iterations. I may execute only one. I get in there and I break immediately. I may execute n. I may execute all n squared. I don't know, right? And so it's important to think about what we actually mean when we say on or on squared. What the big O notation actually refers to is worst case running time. And I shouldn't really say that that's what the big O stands for. What I probably should say, and again, you really want to go read up about this if you want to be very specific. I don't get very pedantic about these things, but if you want to, you're going to want to go read everything, right? But what I should say is when people throw around the term O(n squared. When an average programmer says that to you, what they mean is the worst case running time of this algorithm is O(n squared or O(n), whatever the O is that they said, right? So O(n) means worst case running time. That means in the case where this break gets hit as late as it possibly could, given all possible inputs this thing accepts, how long will it run? Okay, it's n squared, right? That's the worst case. Sometimes through, it might be better. It might be better than O(n squared. So it doesn't mean when I say that something's O(n squared, I don't mean that it always takes O(n squared. I mean that it might. And again, the reason that we typically use that as the metric is because we're talking about scaling. We want to know how this algorithm scales. We don't care how it performs, because that's a different discipline. We care about what we can guarantee. How does it scale in the worst conditions? Because that's what we want to know about. That's what tells us how heavy this algorithm can handle, right? The worst case, that's what we're looking for. They don't only look at those. There's things that are like best case running times, right? There's things that are like average running time. And this is typically called expected running times. Meaning, well, the worst case is O(n squared, but we expect it will only be O(n). What does that mean? Well, might not be that appropriate for a game, because maybe you will hit that case, the bad n squared case, but it might be just fine for an offline utility because most of the time it'll run fine. And as a little amusing side note, one of the things that typically happens with these expected ones is there's a whole branch called randomized algorithms, which are designed exactly for this purpose. They don't care how bad the running time of an algorithm is. They only care what its expected running time is. The worst case is not relevant to them because they employ random techniques to ensure that if you ever did hit the worst case, you would just stop running it, re-randomize, and run again when you won't. There's a whole theoretical branch devoted to just these. They're called randomized algorithms, and it's a great thing to go read about. It's not that applicable to games necessarily, but it is great to read about, and it's a good thing to know. So I would recommend taking a little detour into there. If you're the kind of person who's curious about stuff, I would highly recommend entertaining yourself for a little while by reading about randomized algorithms, because it's pretty funny. And they're useful. Like I said, for offline tools, very, very useful. All right. So there's other things that they talk about, and you will see these sorts of things talked about. And again, what they're talking about there is, well, there's the worst case, but then there's also other cases. So we would like to know that as well. And there are analyses that are done of algorithms that try to analyze what the expected running time of something is, because it may be that certain algorithms are very good, even though they're n squared, because you can almost never hit the n squared case. And so they do care about these other things. It's not just the worst case. That's the only thing a computer scientist might be analyzing. Okay. So now let's talk about a little bit further beyond this now. Let's talk about something you may have seen, which is P equals NP, right? This is something that you may have seen. You may have heard stuff about it like, oh, that algorithm's in P, it's in NP, I don't know, it's NP complete, right? You may have heard even the phrase NP hard, although oftentimes I think most programmers have never heard that, but point being, there's a lot of things there. Okay. What this refers to is actually order notation. And so once you know the O(n), O(n squared, and so on, this starts to come into play. You can understand P and NP totally fine. What they actually stand for is just polynomial and non-polynomial. So something that is polynomial time, right, means that I can write it with a polynomial. I can write its O(n) expression, whatever we want to call that, its big O notation, as you might hear it said, It's big O notation. You can write it with a polynomial. And as you know, a polynomial is anything that looks like, n to the something, like n to, I'm going to use x here to refer to any constant, let's say, or n to the c plus, n to the c1 plus n to the c2 plus n to the c3 plus n to the c4, however many of these you want, right? It's just a standard polynomial from math, right? And you can put constants in front of it as well, whatever you want to do. But it's always got to be n to the something, right? That's just how polynomial is defined, right? So if you can write it as a polynomial where the variable is n, right? I'm not saying this well. This is my math terminology is too limited. If you can write the big O notation as a polynomial where the variable of the polynomial is n, it is in P, right? It is a P algorithm. It is a polynomial time algorithm. Polynomial time because we expect it to scale as a polynomial with the work input. Now you'll note that this could be an extremely heinous expression. Something that was like n to the 12th is still a polynomial time algorithm because I didn't use anything besides a polynomial to represent its running time. So even things that you would never, ever, ever be able to run for any reason because they are absolutely ridiculous, like n to the 12th, are still considered in P. And I often use that phrase, I should explain it. People say these P and NP, I kind of started explaining them without really saying. They stand for polynomial, non-polynomial. They represent sets. They represent classes of algorithms. So if I say that an algorithm, wow, handwriting. If I say that an algorithm is in P, it means that it is in the set P. It is in the group, the class. I'm sure there's a pedantic actual thing you want to say there, but I don't know what it is. It belongs to the class of algorithms that are polynomial time. And that means I can write its order notation with a polynomial. Now, obviously, NP is just the other way round. I can't do that. I cannot write it. So if an algorithm is in non-polynomial, if it's in NP, it means that its order notation looks something like this. The expression, the n, the variable that represents the work units, it is actually in the exponent, right? And at that point, I am in NP. I can no longer say that this has polynomial time. Now, obviously, the difference is pretty drastic. I don't know if like Wolfram Alpha can help us out here with a handy little graph. I don't actually, can Google graph something? Graph n squared and 2 to the n? Can it do that? I don't know how to like get a good graph. I want a graph. Let's try Wolfram Alpha. Wolfram Alpha. Let's see, Wolfram Alpha. How are you going to do, knowledge engine? Can you please graph n squared and 2 to the n for me? Thank you. Thank you very much. Okay, I would like you to expand, please. Can you expand the range for us here on Handmade Hero? Enable interactivity. Oh, we're not subscribed to Pro. How about over the range 0 to 100? There we are. Did that actually work? I think it did. Well, I maybe made my point a little bit too much. Let's try it down a little bit so you can actually see what happens. There we are. So here, if you actually look at the plot, you will notice that 2 to the n is wickedly worse than n squared. It makes n squared, which is already very bad for us, look like a line. It doesn't even look worrisome, right? So 2 to the n is viciously worse than n squared. For those of you who don't have an intuition maybe for how those two things relate, I just wanted to sort of give you a little bit of a perspective into why we care. So yes, P and P, this is tractable, right? This is like intractable, right? Does not scale. You know, these things are horridly bad. You know, you try to feed 100 things to it and it will never run, right? You can't even, you know, forget about it, right? So even though this may look bad, it is nothing compared to this, and that is why we care about what happens to these situations. All right, so what does this whole thing mean? Why do we care about this sort of stuff? You know, what's going on and blah, 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 right? All right, so what I said here, this was a little bit of a perhaps, like, I suspect maybe pseudonym. I don't know if he still comes to the stream ever, but he probably got extremely nervous when I wrote this. You know, pretend I never wrote that. I just kind of wanted to say you probably saw something like that. Let's not talk about that for a moment. Let's talk instead about something a little bit more specific and understandable. Okay, so you know that P is something that's polynomial time, and you know that NP is non-polynomial time, right? Now, the tricky thing about this, and the reason that computer scientists are always so worried about these sorts of things, is that we don't really know that much about how to classify algorithms, or I should say problems, perhaps, into these two categories. You would think that it would be extremely straightforward to say, oh, I've got this particular problem. I know that in order to solve it, I can always, you know, there is a polynomial time algorithm that will solve it, or no, there isn't. It requires a non-polynomial time algorithm, et cetera, right? Well, the reason that you hear things like is P equal to NP or things like that said is because we actually don't know yet how to classify a very large number of actually practical programming problems. So, for example, there's a couple different ones. There's like there's a thing called 3-sat, or circuit satisfiability, I guess, right? I guess I don't know if they just call it SAT. I don't even know what they call them. They have specific names for them. There's a number of problems that are very straightforward. Like, let's say that you have a circuit that just consists of not and AND gates, or you know. In fact, you know what? I'm just going to get what the actual term is. I believe it's 3-sat, though. Yeah. Here you go. So you have a set of problems like this, which when you read it, it will sound incredibly simple, right? It basically says that, let's see if they've got it here. If you have, like I said, ands and nots and any number of inputs, so any number of ands and nots and any number of inputs, they just want to know whether or not you can find a set of inputs that will produce like true or something, right? So for example, again, I don't study this sort of stuff for a living, so I apologize that this part is not going to be the smoothest explanation. But you just imagine you have some expression that's like A and not B and A and, you know, not C and D, and I can just give you any number of those things, right? Well, the number of inputs, A, B, and C, D here, right, is 4, right? That would be the n. The n equals 4 here, right? And the question is, well, I want you to tell me, if you were going to be able to write some algorithm that could tell me whether these inputs here are Boolean, right? They can only be like true, false, true, true, whatever. If you were going to take this and say, tell me whether this expression can ever produce true. You can set these to whatever you want. Can it ever produce true? Naively, you might say, oh, I could totally solve that in polynomial time. Let me just go do it. But then what you would probably find when you tried to solve it is that you couldn't. And the reason for that is because each input can be set to true or false. That means that for each input that you have two options. 2 times 2 times 2 times 2, right? 2 options here, 2 options here, 2 options here, 2 options here. That, my friends, is 2 to the n, or a non-polynomial time, right? Now, if we knew that the only way to solve this was by brute force, we would know that the solution to this problem was in non-polynomial time. It would be in NP, because the only way to solve it would be to try all 2n possible input combinations and see if any of them produce true. But try as they might, computer scientists have yet to figure out whether that's actually the case. We can't prove yet whether there exists some more clever algorithm for processing a thing of this nature that doesn't take NP. Now, we probably know that it doesn't take, n squared time. But remember, in order to be polynomial time, you could write something that takes n to the 256th time if you wanted to, and you would still have succeeded in proving one of the long-standing mysteries of computer science, which is, are these sorts of problems in P or not? Now, when I say these sorts of problems, what do I mean? Well, I mean NP-complete problems. NP-complete is a term you've probably heard. It's almost always not understood properly, and that includes by me. So the explanation I'm about to give you is probably subtly wrong, and you're going to want to go ask a computer scientist to correct it. But what we mean when we say that something is NP-complete is that it is, quote unquote, one of these problems. And one of these problems is a problem, like this one, where nobody has been able to prove that it takes polynomial time to solve, right? No one's come up with any way to solve it, okay? But they have not proved it can't be, so they haven't proved the opposite. They haven't proved that you can't solve it in polynomial time. And they have proven that you can verify the answer. So for example, if you were to give me, right, like true, false, true, true, you're like, that produces true. I can verify that in polynomial time. So this has a p verifier usually, right? It has the ability to verify the solution without also taking NP. Again, there's probably something subtly wrong with that. Like it's like, oh, it doesn't have to have the p verifier. It's called NP complete, frou, if it's like got the p verifier and not. If it doesn't, like I said, go check the specifics. I am just trying to give you a foothold to this so that you can go explore more. But point being, NP complete problems are ones that we don't know where they land. No one has proven either, but we do know that they can be verified in p time. Right? So we can go through here and actually say that the answer was correct or not without needing NP time. Now, the number of problems that fall into this category are actually fairly large, and people have done a tremendous amount of work proving that they are all equivalent. What that means is that all of the problems that are in NP complete, and there are many, the Dean's List problem is another example. I'll just rack them up here so you can take a look at them. Or not. Is that here? All right. Well, there's a problem called the Dean's List problem. I don't know. There's a problem about trying to make sure that no two people sleep in the same room with other people. As far as assigning rooms to people in a college, but blah blah blah. And it's like you have a list of exclusions, and you have to come up with, picking people to share the same room at a college without ever violating a list of things that say two people can't be paired with each other for some reason, right? There's a number of problems like that are all very reasonable, that all sound very logical, that sound like the kind of things you want computers to solve. They have all been proven to be NP complete, which means you can verify the answers in p time, but you cannot actually solve them in p time yet. But until someone proves that you can't, we don't actually know. And that's one of the interesting things about this problem, and why it is such a thorn in the side of computer scientists, is because we would like to know. We would like to know definitively whether we're just missing the big point here, and that all of these problems actually can be solved in p time, or whether what seems to be true, because no one's ever found a p algorithm for any of them, it seems to be that they aren't, right? And the nice thing about all of the proof work that they've done so far is because they've proved all of these problems are equivalent, What it actually means is that if you found a p solution, a p running time algorithm for any of them, any of the things in NP complete, you will have proved that all of them are solvable in p time. Because computer science has actually done the work of proving that you can map one to the other. They're all in the same, they can all be solved by just translating them into like 3-SAT, for example. So if you can solve any of them, you can solve all of them. Now, typical gotcha. And I've heard this I've seen programmers post videos where they make this mistake. Try not to make it. Like I said, this stuff is very complicated. I've probably already made a mistake, but just so try not to make mistakes about this if you can. But it's complicated for non-computer science people. It's true. There is a gotcha. Don't assume that something is NP complete just because it is hard. For example, the traveling salesman problem. Right? That is a problem where I have some Euclidean array of points, let's say. Doesn't have to be Euclidean, actually just have to have costs between them. But so forget I said that. Traveling salesman is really just some set of nodes in a graph. And then I have some edges in that graph. Right? Something that looks like that. And each of the edges has a cost. Right? I could even make all the costs 1. Doesn't even matter. So let's say it doesn't even have a cost. It just costs 1 to traverse, let's say. Because I don't even think you need a cost, but either way. I'm pretty sure the problems are equivalent. Find the shortest path that visits all the nodes, right? So again, it's just like a salesman. A salesman wants to go to each of these places, and they want to see them all once, and they don't want to like waste any time, so they want the shortest possible route that will do them all. That's a traveling salesman problem. It is not NP complete. It is actually harder than that. The reason for that is because there is no p verifier for it, right? There is no way to actually verify the solution to the traveling salesman problem in anything other than also NP time, right? If I were to give you a solution and say, hey, I solved this particular traveling salesman problem for you, here you go, happy birthday, you'd be like, thanks, but that does me absolutely no good, because in order to verify it, I would have to go solve it myself again using another NP-complete algorithm, right? Or sorry, not NP-complete algorithm, using another NP algorithm, right? And so it is not like these other problems, because these problems, you can verify solutions to them. You can verify in p time whether a particular set of inputs does or does not do the thing you said it should. And things like the traveling salesman problem do not have that criteria, right? And so it's important to understand the difference between those, because there's essentially, I don't know that you want to call them a harder class of problems, but there's definitely a difference between problems as you sort of go through there. And I believe that that is typically NP. I think that's NP hard, but this term is also almost always also wrong. So let's see if we can do it. NP hard and see. Firmly, at least as hard as the hardest ones in NP. NP hard when every problem in NP can be reduced polynomial H. Find a polynomial to solve any NP problem would give it polynomials for all the problems in NP, which is unlikely to be considered hard. Non-polynomial, blah, blah, blah. Yeah. Let's see. This is going to be too hard. Class problems which are at least as hard as hardest problem in NP. Problems that are NP hard do not have elements of NP. Indeed, they may not even be decidable. Class problems that contains the hardest problems in NP. Each NP problem has to be NP easy. Let's see, NP equivalent. You can see why this is annoying. Let's see. Polynomial. I don't know why I'm checking this, because I said that someone in mathematician. Yeah, okay. So any NP complete problem can be verified quickly in polynomial time. So that part is correct. I have not made a heinous misstep there. And I believe the NP hard, so I don't really know, I guess. I'm going to take this. I'm just going to say, again, to avoid being one of the programmers who puts up yet another stream with bad information, let's just say that we don't know what that is. Let's just say we don't know, because I think that's safer. But point being, traveling salesman problem is definitely different than one of these. And so what that means is there's a set of problems that are very, very difficult, but that may not necessarily be exactly the same as these kind, right? Because there are differences in the problems that don't necessarily relate strictly to whether or not we know that there's an NP, whether there's a non-polynomial time or polynomial time solution for them, okay? So that's just yet another aspect of that. This whole thing here with the different categories, it looks like this is a pretty extensive taxonomy here. So like I said, if this is the sort of thing that interests you, you should definitely go read about it. There's a lot of interesting things in there. It's not the kind of thing that I spend much time doing, and so that's why I say I'm the wrong one to give you any more, right? Once you get past what I've just told you, that's the end of my understanding. What's on this blackboard here is all you get from me. I don't study it. I don't know. But again, like I said, it's kind of interesting. It's interesting, like I even find this part interesting. That's like, oh, there's problems that we can actually verify very easily and problems that we can't verify very easily, but both have the same sort of like NP-ness thing to them. And I don't know, that even just that alone, those sorts of things I find very interesting. So I could easily see spending time doing it, just doesn't come up at all in what I do for work. And so I've never really had time to say I'm going to spend several months really getting interested in this sort of stuff and like playing around with it. But that's all the basics. That's everything. Okay, so let's bring it back around now. I've sort of given you a tour through stuff I don't know, right? I told you the stuff I do know. I've given you a tour of stuff I don't know, so if you are interested, you can go, sort of do some home study on this stuff and maybe get into it. Maybe you can learn a lot more about than I do and teach me some stuff. But now let's bring it back down finally to our goal, which is sorting. Okay, so sorting, why do we care about this? Why did I pick sorting as a time to bring up this order notation stuff? Why are these related? Well, sorting is kind of a classic example of why you might care about order notation, because typically sorting is the kind of thing where, if done poorly, is n squared, right? The reason for that is because it's inherently talking about taking a series of things and putting them in order. In order to put things in order, you have to compare them. And whenever you're comparing two things inside the set, you end up with a pairwise thing, kind of like the envelope problem I talked about at the beginning of the stream. I'm looking at an item and another item, figuring out how they are different, and then making a decision. Then taking another pair and another pair, and anytime there's a pairwise thing, you're getting into an n squared situation. So, sorting is a very studied problem for this very reason, and there are many algorithms which attempt to do better than n squared at sorting, because naively you would expect it to be n squared. And lo and behold, if I go ahead and open up the one that I wrote in just a few minutes the other day so I could show you how sorting works in the basic case. What is the running time of our sort? You will notice, hopefully based on everything I've told you, you can see right away it is itself n squared. There is count minus 1, that is count squared minus count, or on count, basically. The n equals count, so on squared. Let me see if I could say that a little bit better, right? We have one loop that goes to count, one loop that goes to count minus 1, right? And so if I'm going to run those two, that means I have to do count iterations of count minus 1 things, or count squared minus count, right? And that means my order is that. And like I said, I don't really care about extras here. I care about the scaling, so I just care about really the highest exponent. So I would just say, and again, these are our n, right? I would just say it's on squared. right? It's really O(n) squared minus n, but I don't care about that because that doesn't affect the scaling at all, right? So it's this right here. And so just like I predicted, if you don't do anything smart, you end up with n squared, which means this won't scale. If you wanted to render 1,000,000 items, you would be sitting here all day waiting for the entries to get sorted. Thankfully, we're not, so we don't have to worry about it right at the present time, but that is what would happen. Okay? And so what happens with sorting algorithms, right? Oops, where's my actual, there it is. So what happens with sorting algorithms is people have tried to figure out how to make sorting not be n squared. And so a lot of the algorithms that people tried to come up with, right, they're just ways of figuring out, can we do something clever and not have to spend n squared time, not have to compare elements to other elements. Now, that may sound impossible at first if you've never considered it, but the reason why I could do that is because let's say I wanted to do something like, I don't know, let's say I wanted to sort to be honest, I guess I can't give you a really intuitive reason for why you can do this. So I may just have to kind of explain an algorithm and then show why it isn't. I'm trying to think if there's any intuition you could apply that would let you go, oh, I see how you would approach this if you've never seen one before. Yeah, I can't really think of one. So let's go ahead and do it this way. Let's talk about how we were doing our sorting before, and then I'll show you some other ways we could do it, right? So before we had a situation where we sort of said, oh, well, we've got A, C, Z, D, Q, right? This is my input, and I want it sorted. So I want you to give it back to me A, C, D, Q, Z, right? And in the naive case, if I'm just going to compare every element with every other element like I was doing in my bubble sort, where I just kind of would bubble things up. And in fact, I could make this actually hit that case pretty trivially by just doing it this way. B, C, D, A, right? And maybe I'll put a few more in there. B, C, D, E, F, G, A. My bubble sort, because it can only move the A one place every time, will actually take the whole n cycles to do it. So it'll do n times through n passes, right, to move the A all the way up to the beginning. So it actually will run n squared. So our current sort, our bubble sort, will literally take O(n) squared time, even if we early outed. So even if we did this to do here where we said stop if the list is already sorted, so you don't have to keep going, we could trivially feed it something where the frontmost element is all the way in the back, and it would take n squared time to produce A, B, C, D, E, F, G. Right? But we can do potentially better than n squared worst case running time by observing that if we were to partition these things into smaller groups, oftentimes it's called divide and conquer is a strategy. There's also another one which is bottom up, which is called dynamic programming, and these are various different strategies for algorithm design. They're very important. They're not something we really cover on Handmade Hero, but maybe eventually we'll get to them when we have to do some more complicated things. But divide and conquer is basically a strategy for devising algorithms that says, well, if something's really hard to do, let's just keep breaking it into smaller parts and see if breaking it into the smaller parts allows us to do it in any faster time, right? So here's one example. Let's suppose, and you know what, I'm going to go ahead and add an h in here just so I have an even number for now because it makes it a little easier on myself. Let's suppose I broke this into pairs of 2, right? So first what I did is I just segmented it like this, okay? And then I said, I just want you to sort the pairs of 2. How long would that take? Well, I need to compare these 2 items, right? So that would be 1. That would take 1, right? I need to compare these 2 items, so that would take 1. I had to compare these two items, so that would take 1, right? I need to compare these two items, so that would take 1. Depending on how we want to count it. Maybe we'd say that counts 2 because we had to visit both items. Doesn't matter either way. It's just going to either be double or single the running time. But either way, however you want to count it, we'll just say we'll say it's 1 for now, because we'll say that our ON is in the comparisons, right? It's how many comparisons you needed to do, right? Okay, so that's how many comparisons I would have to do this, right? And, well, you know what? It would help if I started with the right list. I need one that's out of order first. Let's try that one more time. Okay, so I check these two, that's 1. 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 And you notice I reversed the order of these two because they were in the wrong order in the list. So that was what I was, these all stayed the same, but this one changed, right? So I can do one pass, essentially, and get all my pairs in order. Make sense? Now, if I wanted to, I could then combine any two pairs, right? I can funnel these guys together because I now know that the pairs are in sorted order. So there is no chance that if this guy, right, if I compare this guy and this guy, there's no chance that this guy could be anything other than in the same direction as this guy during the comparison, right? I know what direction they go. So what I can do is I can say, well, let's produce a list here. I know I only have to check these two to figure out who comes first. I don't need to check either of these because they can't possibly come first. The person who's in their own pair comes before them. So if I check these two and I say, oh, B comes first, I'll put B there, that's one comparison, right? I then say, all right, move to the next guy, compare these two. Okay, C or D, which comes first? In this case, it happens to be C. That's another one comparison, okay? Then finally, I would move to here and I'd say which one comes first, C or E, right? And that's again one comparison. And so then I end up with that, right? Oops. So I only needed to do 3 comparisons, whereas if I had done all the pairs, BD, BE, CD, CE, right, I would have had to have done 4 comparisons. Make sense? So I shaved off one comparison just by taking advantage of the fact that I know these are sorted. Do the same thing here, right? F, G, A, H, right? Let's do that one. So I take this one. Is F or A first? Well, A is first, right? Now I move to H. Is F or H first? Well, F is first. Now I've got G or H. G is first, and then and of course H, right? So that was 3 comparisons again to get 4 results, okay? So now you can kind of see as I lever up here, right? I've done effectively something that's only on the order of n here, basically, and something that's only on the order of n here as well. I've never had to do a full pairwise thing still. Let's take it further and you can see how much more powerful this gets when we have the bigger sets. Let's go together, right? How many comparisons for all of these? Well, B and A, which is first? A is first, right? Now let's go to the next one. B or F, which is first? B is first, right? So that's one comparison, right? It's one comparison basically for every one I write, essentially, yeah? Okay, so B, where am I at here? I did B. F is first. F isn't first, so we go down to C, right? C or F, it's C, right? So then I can advance ahead. D, D or F, it's still D, right? Then I go to E, E or F, it's still E. Then I'm out. So now I just know that I just do the rest of these, right? So then I'm just G and H. Because they're just in order, I just copy them, right? So hopefully you can see how few comparisons I've done. I'm already at the end of the list sorted. Now, if I was to do this n squared, right? 1, 2, 3, 4, 5, 6, 7. Wait, that was A, B, C, D, E. Oops, forgot my F. A, B, C, D, E, F, G, H, right? This list, if I was to do this the n squared way, that would have been 8 squared, or 16 comparisons, right? Make sense? In this case, at most, I only have to ever compare the number of things that are in each of these lists, the number of times up that I had to do these steps, right? So I have to do n steps potentially, right, or something on the order of n, but I only had to do it 3 times, right? So even though I gave it n inputs, instead of n squared, I actually just had, you know, n time, excuse me, I actually just had 3 times n. Make sense? So this is much, much better than this would have been, right? This is like much better. And I guess I'm using the order here because it wasn't actually 3 times n, it was nowhere close to that because we're actually counting the actual comparison. So, you know, it was, instead of n here, it's like, how many did we do? We did like 6 here, we did 4 here, so 4, 6. We did basically like something like 14, right? Now, it's a little bit tough because, hey, that only looks like it beat it by 2, which is not that great. But hopefully you can see as you would go up here, things would get a lot better because every time I moved up, I was only having to do I was only having to do a number of comparisons that was based on the number of things for those numbers of steps. And how many numbers of steps would I actually have to do? Well, if I start with the lowest level, which is every 2, right? Then that's just going to be 2, you know, for, it's going to double every time, right? It's going to be 2, 4, 8, 16, 32, right? As I go up through here, that's how many I was processing each time. And what you can see there is that's essentially just a power of 2 that it increases. So whatever n was, in this case n was 8, we just have to take essentially the log root 2, right? We just want to say what, you know, 2 to the x equals whatever our n is, right? Or log, excuse me, log 2 to the x equals log n, right? Makes sense? So I only need to take whatever the log 2 is of my input n, and I would get how many of these steps. In this case, it was 3, right? What that means is the running time for this thing, instead of being n squared, which is what we had before, if I was to use this method, I would end up with something where we took the log of n, right? And then it was times n, right? Because I still have to do something on the order of the number of elements each pass through this thing, if that makes sense. And that actually is a very common running time to see, which is written like this, n log n, it's called, right? Which is any time you have some kind of a binary divide and conquer algorithm where you're doing n things on every pass, but you only need to do as many passes as the power of 2. What you've essentially done is you've taken something that was, you know, O(n) squared I could write as O(n) times n, right? What you've done is you've taken, normally I was doing n passes, in fact I could even draw this out for you. Normally what I'm doing is I'm doing this, right? I'm taking every possible combination of the n's and I'm doing all those possible comparisons, right? And instead what I've done is I've attacked one of those n's, one of the loops, instead of one of the loops being going through the entire n, I've changed it to a log n. So now I've taken something that was n times n and I've changed it to n times log n, right? And so just to be more concrete about it, right, you could imagine pulling this out into something that made a little bit more, that was, you know, sort of longer or had more, you know, got up a little bit higher, right? So A, B, C, D, E, F, G, H, I, J. This isn't going to be small enough. K, L, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, N, M, O, P. There we go. So now I got 16, right? 2, 4, 6, 8, 10, 12, 14, 16, right? Now, in order to do our bubble sort, we know exactly what this would look like in terms of how many times we'd have to process this. We'd have to process this many things, and we'd have to process it n times, right? So we'd have 16 passes through the whole thing, right? So we'd have, you know, this is our first pass, second pass, third pass, fourth pass, fifth pass, sixth pass, seventh pass, 8 pass, dot, 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 right? That's how many operations we'd be doing. But in the way that I just talked about, now what we do is when we order each of these, we then move up to one that has twice as many elements. So the next phase is A, B, C, D, E, F, G, H, I, J, K, L, N, M, O, P, right? And the next phase after this is, let me see if I can get it right underneath the number there, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Don't ask me why I wrote those in opposite order. And the final step is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. And so what you can see is that in the log n case, with 16 inputs, after just 4 steps of the O(n) part of the algorithm, I am done, right? But if we had done the bubble sort, we would have had to go all the way out to 16. That's over here, right? That we'd still be running. And so the 8 case, I kept it small so you could see how it was working. It doesn't show how much more powerful it is because it doesn't have enough. But as soon as you get more, you can see, right? Whereas the bubble sort would have had to run each of these times. It would only have been a quarter of the way through its process by the time the this one's already finished in terms of the number of steps, right? So that's why this is, again, n log n. It's because it does have to look at essentially, it has to do it work proportional to the items, but it only has to do that work log n times. So if n is 16, well, obviously 2 to the 4th equals 16, right? And so that log n is 4 in this case, 16 times 4. Whereas our O(n) squared algorithm, right, that is a 16 squared. That is a really nasty amount of work. That is 256, right? Yeah, I'm not wrong about that, am I? Yeah, 2 to the 4th times 2 to the 4th is 2 to the 8th, 2 to the 6th, right? So we've taken something that would have been 256 in the bubble sort case, and we've changed it to something that in this case is only going to be 64. And that's a pretty darn good savings, right, in terms of the number of work units. And so hopefully that gives you some sort of insight into why we would care about stuff like this. The nature of the algorithm and how it processes the inputs can have a very real effect on how this works. Now this, I believe, is typically called a merge sort. It actually has a name. And it's called a merge sort because it does exactly what its name sounds like it does. It takes little pieces that it knows to be sorted and it merges them. And then it merges them again. And if you can't quite figure out, because it is a little confusing, where the secret sauce comes from, why is it able to do it so much more efficiently than the bubble sort? Well, the reason is because it reuses comparisons, right? It's basically saying, oh, hey, guess what? In this particular case, I know that since I've already compared these two, if I compare one of these to one of these, I then imply something about the other one in that pair, right? And that actually, I know I said this, we're kind of getting off on a tangent here, but I'll just say that is actually the basis of dynamic programming, which is a whole another discipline of programming, which I would also encourage you to look up if you were interested. Anyway, point being, that is called a merge sort, and it's an example of how we could knock down the worst case running time of our bubble sort quite considerably just by doing something very, very simple. Hopefully you understood exactly how that would work. It's incredibly, incredibly basic. Now I've only got 4 minutes left, so I think what I'll do is I'll reserve a little bit of time for questions. Hopefully that was a reasonable introduction to how this sort of stuff works and why you might care about it. Again, as it applies to sorting, the choice of algorithm and its complexity determines how, when you add more elements, how much work you will actually have to do. And this, as you can see, even with just a small number of elements, will probably be much faster than our bubble sort if we decide to do it. And that will be the subject of tomorrow's stream. We'll be talking about some of these sorting algorithms and implementing one of our choosing, possibly merge sort, because it's kind of clean and nice. But we could also do quick sort, which is dirtier and a little less predictable. But let's go ahead and go to the Q&A here so I can see if people have questions. Quartertron, NP stands for non-deterministic polynomial, plus some other minor problems. Otherwise, well done. Okay, good. So we have a good correction there. No one will know if I just change that. There we go. You know what? That's good. And in fact, that's something I should have remembered, because that's actually, if you're actually in NP, you would assume that that would mean that you absolutely knew for sure, right? So non-deterministic is way better because, you know, that makes sense. If you say non-deterministic polynomial time, it's like, now you actually are saying we don't know. The fact that we don't know is right in the name, right? That makes sense. So yeah, so that's better. So the only question is, how do you say non-polynomial? If you can't say NP, what do you say? Because if NP meant non-deterministic polynomial, like, how do you actually say, like, how do you say the thing that I was talking about? How do you say that? Can you just not say it? I mean, you can't abbreviate it? Let's see. For the record, the remark I made earlier about restaurant sorts also isn't merge sort n log n. Yes, that's the one we're talking about down here. This is merge sort, and it is n log n, right? That's what we said right here. Long Boolean. So unit testing a function that computes a path for the traveling salesman problem would require writing the algorithm twice, the second one testing the first. Yes, actually, unfortunately, yes. Unless you solve some open problems in computer science. I mean, as far as I know, traveling salesman, there is no polynomial verifier for it. And so you can't test its results, if that makes sense. You would need to, yeah, there's really nothing you could do as far as I know. Five Shot 97. Do you think computer science major is a good path to go? I'm in it now. I don't know. It depends on what it interests you, right? Like I said, you know, well, as the fact that I got the NP term wrong here, and then I actually, and I still don't, so let me ask again, just in case someone knows. How do you actually say non-polynomial? Is there no abbreviation for it? Like if I actually want to talk about something that's non-polynomial time, I don't want to say non-deterministic polynomial. I want to say non-polynomial. Can you say anything? Is there a name for it? Like, can you say QP or something that means non-polynomial time? Or is there just abbreviation NP and that's the only abbreviation and it only means non-deterministic polynomial? So if you want to say non-polynomial time, you have to literally say non-polynomial time. Insofar as says you say exponential, and okay, it sounds like Busy Beaver, Huge Mung, and Strophium are both saying not in P. All right. Okay, so basically, let me rewrite this just for the benefit of people who might watch this video later. So here's how we say what I wanted to say. P is polynomial time, that doesn't change. NP is non-deterministic polynomial. And that is what I explained here, which is saying that it has the P verifier, I guess. Well, that just says we don't know. I guess let's leave it at that. That just says we don't know if it's in here or not, right? And then not in P was actually the thing I was trying to say. So when I said NP, I actually really meant this, because I was trying to explain the things that don't have, that are like 2 to the n or whatever, right? For sure it's 2 to the n. So I guess that's all you can say. There is no abbreviation for this guy. Maybe you could call him NIMP. This algorithm is NIMP. I like that. This is a NIMPy algorithm. It is not in P. All right, so that's, for those of you who, like me, don't know computer science very well, that maybe if I can just get that drilled in, I will stop using the wrong terms to refer to things. Because I've never known what that was, and that's good to know. So not in P. I can just say that, and I won't say NP anymore when I mean that something is like traveling salesman. Although I guess we don't know. Have we proven traveling? Let's ask that. Has anyone definitively proven that traveling salesman could not be in P? Or do we still, is that potentially NP hard? Like, is this as hard as NP, but not necessarily NINP? What do we know about traveling salesman? That's the question. Because, right, just again to sort of cement this down, if nothing more for my own sake, we know that traveling salesman doesn't have a P or NP thing that we know of yet. Or sorry, NP complete. We know that it doesn't have a polynomial time verifier, and we know that it doesn't have a polynomial time solution that we've found. But we don't know necessarily what has been proven about it. I'm pretty sure that they haven't proven it NP complete. I'm pretty sure that it is not NP complete. I think because it doesn't have, like I said, I'm pretty sure no one has found a P verifier for it. But I don't know if anyone's proven that it's not in P. Maybe it still is. So do we know? So people on the stream say NP complete, which means that it is, in fact, possible that if somebody were to figure out how to solve NP complete problems in P time, traveling salesman would also be solvable in that time. Meaning even though it doesn't have a P verifier that we know of, here's another question. Have they proven that it doesn't have a P verifier? I really want a computer scientist to just step in here and give us the full explanation, because I'd like to hear, but unfortunately we don't have that. Well, I'll let this go on to the thing. So somebody figure out whether the shortest path problem. I don't think so, because it sounds like what you guys were talking about in the stream is not what I was saying was the traveling salesman problem. Finding the shortest path is different than just finding a path of a certain length, right? Although I guess technically you could transform those by then just asking, sum up all the paths and then take one off, and in order take them off. Although maybe that doesn't work. I want someone, so on the forums, if one of you computer science folks would be kind enough to do so, I would love for someone to post some information about traveling salesmen, right? Because I would like to know if we've ever figured out whether it has a p verifier. Because I thought it didn't, but maybe it actually does. Or maybe it does now, and it didn't before, or something. So I'd like to know about that. That would be nice if someone could post about that, and I'll take a look at it. Maybe we'll talk about it tomorrow, if someone does post. All right, so anyway, this is all good. Everyone's happy. I'll go back to the Q&A. Oh, I've created a problem, I guess. People don't know which traveling salesman problem we're talking about, so there's more than one. Interesting. All right. Let's see if there's any other questions here. It scares me that people on the stream who I think are CS people are not even able to agree about the traveling salesman problem. I feel like tomorrow should just be called 10 minutes traveling salesman problem. Queen Sab 3, wouldn't saying that something is NinP imply that P is not equal to NP? Did we win a $1 million prize? No. So again, like I said, this stuff is outside of my area of expertise. So I would hope to refer to you to some place that's better to learn about it. But the reason that there's P, something is in P and not in P, the reason that that's not the same as non-deterministic polynomial time or whatever, the reason for that is because it's possible that you could prove that there are things you cannot solve in polynomial time, right? Maybe you can prove that. So you might be able to prove that an algorithm is not in P. That's just for one specific problem, right? So, maybe it's like the, we make up some problem. We have the magical sorting foo problem, and we figure out that that problem is so hard that there's no way we can prove that it's definitely not solvable in polynomial time, right? It's non-polynomial, period, right? I mean, I guess I could do that. Can't we just do that? Write all the numbers, from 1 to 2 to the n. I mean, it's not very computer science-y, but there's no way to do that in polynomial time. You have to write them all. You're done, right? It's not really valid, but imagine you had something that was that blatant where you're just like, yep, there's no way because the amount of work that actually has to get done is the 2 to the n, right? This doesn't really count because you might then say, well, that actual number there is n and blah, blah, blah. So maybe that's bad. But if you could find something that you could actually prove, there's no way you could do it in polynomial time, that's saying it's not in P. The problem with the NP complete things, saying NP complete, I believe, is saying that we've sort of proven that it's in this set, the non-deterministic. I'm going to write this so I don't forget it again. My brain's getting old because it's not like I didn't know that term, but I guess I'm just getting too stupid. Anyway, non-deterministic polynomial time, this is a class of problems that we couldn't prove that for. We don't know how to prove this for it yet. So it's not so much that P and not in P, it's not so much that you can't ever classify algorithms into one of these two. Oftentimes you can. But there's a whole set of algorithms in between that we don't know. We just don't know. The proofs are too hard, or not possible, or who knows, right? For some reason, nobody's been able to prove it yet. And so that's why there's like room in between here for the NP complete stuff. And we just don't know. So I don't think it's necessarily impossible to do this. You could prove something was not in P. But for these things, nobody has ever done that. They've never proven it in either direction. They can't prove that it's in P and they can't prove that it's not. It's just in limbo. I think everyone sort of expects that eventually we will prove that it's not in P, but no one's done it yet. Long Boolean is suggesting that the game should include a traveling salesman. I agree. Kubrick Caleb, will we go into more complex sort algorithms like radix sort? Also, is the space requirement of merge sort something that needs to take into consideration for Handmade Hero? So we have plenty of space, so I don't think it probably would be. As for radix sort, I don't know. We've got floating point numbers, so I don't know that radix sort is going to be particularly useful to us. Maybe it will be. But radix sort is kind of a very special case sort of a sort. It's not very general purpose because it implies some very specific things about the inputs that is not so good. It makes it hard to sort on things other than very specific numerical things. Quartertron says, since you didn't go to college, when did you first get interested in, or at least start learning all about Big O? I think it was because I had a book called Introduction to Algorithms that was just about like sorts and disjoint set forests, all sorts of weird algorithm things, and it talked about it a bunch. So I was like, oh, okay, like I see you, right? But as you can tell, nobody makes this mistake that I made up here where I was like tried to refer to non-polynomial time by saying it was NP, right? Like nobody makes that mistake if you do a lot of computer science. So you can tell I hardly do any of it. I only know it just from the very basic, conceptual stuff like here where you look at an algorithm that you write and you go, what's its complexity, worst case complexity, because that's very easy, right? That's the very practical, very simple part of the computer science. But any of the other stuff I don't know. And like the non-deterministic polynomial time stuff, I find it really interesting. Like I'd be super entertained going and studying that, I'm sure. But I've just never done it. So I know almost nothing. Like that's why I say like I don't know anything about like even which problems are in there. I remember like Dean's list and 3SAT, but there's dozens of other problems that they proved are NP complete, and they do mappings between them and all the other stuff. I don't know anything about them, other than I think it's pretty cool. Insofar as says, I'm not sure we can prove something is not in P unless it is undecidable, or we can prove P is not equal to NP. So maybe that's true. Again, like I said, I don't know. My computer science knowledge is way too... Connor Rents, by the way, 8 squared doesn't equal 16. Did I do that somewhere? Nice. No wonder this looked... No wonder this looked not so good. 8 squared is 64, so that compared to whatever it was, 14, is a lot better, right? So I guess we didn't have to do... if my quick math had not been so bad, I guess we didn't necessarily have to do all these. So it's bad even... It gets bad really quick, doesn't it? Man. N-squared algorithms are just really dangerous. That's really nasty. For obvious reasons. But anyway, thank you, Connor, for correcting that. I'm really enjoying. So I kind of like, seriously, guys, I really want someone to. Can we start a forum thread on this? Because like just the amount of argument that's in the chat over whether or not you can prove stuff is NP or not is kind of entertaining. I would love, in fact, all we really need, if there's a good explanation for this somewhere, like you go to the Wikipedia and like it's just dense nonsense, right? Like you go to something like MP Complete and you get a lot of stuff that's just really hard to actually follow, right? Where like they have stuff that's just not a very intuitive explanation of what is actually going on, which may be fine if your primary goal is like mathy, right? But if you're just trying to understand the basics of it, it'd be really cool if I could point people on the stream, like tomorrow or something, when we actually go write the source stuff. It'd be really cool if I could point someone to something that's like a really good introduction where it's just very clean, you know, explained. If you explain the way I was sort of explaining it here, where it's just very like intuitive and simple, but someone who knows the real deep parts of it, so it's all correct and has all the right interrelations and there's no mistakes, you know, like and it has the stuff like, can you prove things, like examples, you know, is there somebody who has like, oh, and here's an example of something that's not NP, right? It'd be really cool if there was a place that people could go for that. I would love it. And I feel like other people on Handmade Hero would like it too, just so that people who are curious about that can basically like go and get the primer that just lets them know what this is all about without having to actually learn it all first, right? So yeah, because that would be really, really great. It's something I've always wanted too, because like I said, I don't ever have occasion to study this and it doesn't really affect me, but it's intellectually interesting. And so I feel like there's a lot of people who would benefit, who are like curious, who would benefit from having the really good version, you know, an hour or two lecture even or whatever, that's just like, here you go. That would be pretty awesome, if that makes sense. Quartertron says, I shall dig through my copy of Computers and Intractability by Gary and Johnson tonight. Well, thank you very much. Quartertron, the first sentence contains the word whimsical, so it's looking good so far. Okay. Long Boolean has posted a link.
The following content.
Introduction to Algorithms Computational Complexity by Eric Deman. I will watch this tonight and see what I think. All right, so I think that's about it for today. Yeah. Anyway, just to wrap up after all of that. So all of that was, you know, like I said, just tons and tons of stuff in there from computer science. If you want to know more about that, I would definitely encourage you to go take a look. It is not something I ever do much of. So I would definitely encourage you to study it on your own or learn more about it if it interests you. If it doesn't interest you, that's fine, but this stuff you still gotta know. So the part that you have to know, you gotta know this basic stuff, the stuff that I sort of worked through. You've gotta know these things. You wanna be able to tell the difference between these types of algorithms, right? You wanna be able to know, did you write something that's O(n)? Did you write something that's O(n)²? Did you write something that's n log n, right? And basically, like, if you don't know the complexity of your algorithms when you write them, you won't know how your stuff scales as you add more entities to your system, more triangles to your render path, whatever it is that you're trying to handle workload-wise, this stuff you gotta know. So like P, NP, stuff like this, you don't have to know that. It's interesting, you don't have to know. This stuff, you do. You really gotta know this. It's not hard, right? It's not nearly as hard as like halting problems or NP complete or any of those things. It's not nearly as hard as any of that. It's much, much simpler, but you do have to be aware of it. And so this is the stuff, again, that we'll go over for a second time tomorrow, where we just actually implement a few sorts, look at what their running times are, and just kind of hammer home the reason why you care about this. So yeah, hopefully, maybe you're a little interested in this stuff, and maybe you'd like to take a little bit of a look at it. That will probably never come up again on Handmade Hero. But this stuff absolutely will come up. I've already mentioned it many times in the past. I will mention it many times in the future. And you really do have to be solid on this stuff because, again, not that hard. Does not require really any theoretical knowledge. It's just a very simple, very basic concept of can you figure out the maximum number of loop iterations your thing is going to do. And that's something every programmer should be able to do. It's not theoretical at all, actually. Obviously, it has a lot of applications in theory, but in terms of using it day to day, it's very practical and very, very worth knowing. Because if you don't, you end up with a lot of surprises. Things that you weren't expecting to hurt you can hurt you a lot as you try to scale up your game to handle different sizes of worlds or workloads. So very, very important there, and I hope that, again, that's kind of a little bit more cemented now. Tomorrow we'll go back and just start focus on writing some sorting code, and we'll look at the complexity of that sorting code. First our bubble sort, and then maybe we'll write a merge sort like the kind I demonstrated today. And we'll talk a little bit more about that to make sure that it's really solid in your head. That's about it. Let's sort of put an end here to that. Let's close that down. There we go. Thank you everyone for joining me for another episode of Handmade Heroes. It's been a pleasure blackboarding with you as always. And thank you to the folks on the stream who maybe sort of tried a little bit to answer our NP and P questions, but I kind of am trying to assign them some homework. For those of you on the stream who are good at computer science, if you would be so kind as to go and click on our little forums link here and maybe go to the code discussion place. If you could post some resources there, I know I would certainly love to have a more solid walkthrough that I could watch myself, but also just point people to. If the stuff they saw on tonight's stream, they were just kind of like, I would like to know more about some of the crazier aspects of what goes on out there in computer science land. Something that was a good introduction, not too difficult to get into for people who aren't on that track necessarily. That would be really awesome. So if someone could do that, I would really appreciate it. And I will check it before tomorrow's stream. And if there's anything good up there, I will talk about it and point people towards it tomorrow. All right, that's about it. I will see you guys back here tomorrow at 5 p.m. Pacific Standard Time for some sorting code. If you want to always make sure you can catch it, we've obviously got the tweet bot is tweeting its little tweet out. So if you want to check to make sure you can catch it live, just head there. Otherwise, I will see you back here tomorrow at 5 p.m. Until then, take it easy, everyone. Have fun programming and have fun CS researching. Take it easy.